Hello, everyone, and welcome to today's webinar. I'm Nathan Tracy. I'm a technologist on TE Connectivity's System Architecture team in the Communications Business segment. And for the next 90 minutes, I'll be serving as your host on this Tech Talk webinar on cloud data centers. Joining me today, we have a distinguished panel of technical experts from TE Connectivity who are all engaged on a daily basis to develop new products and new technologies to support and enable next-generation data centers. So joining me on today's Tech Talk webinar will be Aaron Byrne, who's our Chief Technology Officer and Vice President of Engineering, Dave Helster, who's an Engineering Fellow in our Data and Devices Business Unit, Mike Trice, who's an Engineering Director, also in Data and Devices Business Unit. Jonathan Lee will be one of our participants. He's the Senior Engineering Manager in charge of our bulk cable development activities. Joe Richard is from our Energy Business Unit, and he is a Business Development Manager there. And then finally, Chris Blackburn, who's a technologist in our System Architecture team, like myself, also in our Data and Devices Business Unit. For those of you that are new to TE Connectivity, we're a global industrial technology leader in sensor and connector technologies committed to unleashing the potential of every connection. Our 8,000 engineers serve customers in more than 150 countries. In fact, we manufacture more than 270 billion products each year to enable high-tech applications that are advancing the future of transportation, making factories and homes smarter, enabling global communications networks, and revolutionizing medical technology, all moving the world forward. If you're new to our Tech Talk webinars, this series highlights groundbreaking technology and engineering trends with TE engineers and partners. We dive into technology we co-create together to create a safer, sustainable, productive, and more connected future. Throughout this ongoing webinar series, we will look at innovation around the Internet of Things, Industry 4.0, 5G wireless, the future of transportation, and more, like today's discussion on next-generation data centers. For our audience, a few housekeeping items before we begin. We welcome and we want to hear your questions and feedback. You can submit questions through the Q&A box on your screen. We will try to leave about 5 minutes at the end of the webinar to address your questions. In the resource box, you can find links to learn more about the solutions that we'll be talking about today. By clicking the speaker bio icon at the bottom of the screen, you can learn a bit more about each of our speakers, including their email addresses, so that you can follow up with them directly. Also at the bottom of the screen, you can share comments directly on Twitter and LinkedIn. And lastly, within the next day or so, you will receive an email with a link to replay a recording of today's webinar. Now, let's go ahead and let's get started. Certainly everyone is aware of the importance of data centers and cloud data centers. They impact our lives on a daily basis, and I would dare say over the last 12 months, they've impacted our lives on a minute-by-minute basis. The growth in this market has been huge and is well documented, and the outlook is for even more of that growth. For today's discussion, we want to talk about these future challenges and needs, as well as how TE is enabling the cloud operators to continue to satisfy the upcoming requirements. As you see on this slide, we're faced with tremendous growth in applications, which then brings the growth in connections, data rates, workloads, which then causes a huge demand on power, which evolves us to new topologies and new technologies. And we're here to talk about all of that today. So let's go ahead and get started. First, let me throw out a question to Aaron. Aaron, we hear a lot today about the magnitude and the growth of the cloud data centers. But what is TE doing today and for the future to help to enable the cloud operators to maintain their projected growth and to meet their evolving performance requirements?
Thanks, Nathan. TE works together with several stakeholders, including customers, standards bodies, and silicon suppliers, to enable the expansion of system architectures that accommodate this growing demand for bandwidth. We work across the data center ecosystem to understand customer pain points and to help remove constraints that limit the amount of data that can be transmitted or used in these millions of calculations. Roadmap alignment discussions with these ecosystem players keep TE on track to be ready with the next generation solutions as the market is ready to adopt them. As an example, understanding the impact on interconnect products that will be used for artificial intelligence or other new kinds of computing workloads is currently top of mind, and you'll hear a little bit more about that topic later in more depth. In networking, hyperscale data centers continue to expand and performance requirements go up relentlessly. They stretch the limits of data rate and density. The slowing of Moore's law means that switching architectures are becoming more power hungry and thermal challenges begin to dominate the landscape. Here's another place where you'll hear more from the team on how TE is handling some of those challenges later. Back to you, Nathan.
So, Aaron, how do those demands vary for different kinds of data centers? For example, you mentioned hyperscale, but what about hyperscale versus co-location versus the edge? How do you see differences there?
So as we look across the landscape from hyperscale to edge, at the edge we begin to see environmental factors playing a bigger role. Our designs for the edge will be ruggedized for those environmental factors, including needed adjustments for temperature, humidity, or vibration challenges. And then as we compare hyperscale to co-located data centers, the difference there is a little more subtle. Hyperscale architectures are optimized by each customer and finely tuned to extract maximum performance. So custom products are necessary for those types of customers, while co-located data centers are more standards-based. And as I mentioned, the edge data centers prize the rugged reliability. So those are some differences. But overall, it's really an exciting time to be engineering products for this explosion in bandwidth and data center build-outs across those different types of data centers. And my colleagues will be able to explain some of these concepts in a lot more detail. Back to you, Nathan.
Thanks, Aaron. So let's turn to Joe Richard. Joe, talk to us a little bit about powering a data center. That doesn't sound that exciting, but talk to us more about that. As the data center industry, particularly in the U.S., is beginning to shift to IEC standards for powering, what impact will this have on advancing data center design and improving a facility's overall performance, including processing power and ownership costs? And Joe, one of the things to also think about in your reply, is it realistic for data center owners to switch to alternative energy sources like solar and wind power systems? Go ahead, Joe.
And thanks, Nathan. It's not considered the most exciting part, but in reality, it's one of the most important applications of a data center. It's usually the last application because you have to power everything up at the very end. So it needs to be considered one of the most important applications because it can cost the owner massive amounts of revenue if an outage occurs. The typical outage will actually cost an owner $9,000 per minute of revenue. And you were talking about the transition from IEEE to IEC. We have seen a steady increase in owners migrating to an IEC standard switchgear over the last 2 years. It has several impacts on the design and the performance. If we want to talk about the design, it's actually a smaller footprint of gear. So it's about 30% less in size than a typical IEEE metal-clad gear. Most of this gear is going to be called gas insulated or prim set. And what that's going to do is it goes in line with what's inside the data center. The high density racks and the switch gears that go inside is just now migrating to the outside. And it assists the owners with less land acquisition with that. And we'll touch base on that in just a second. But the second part is it's actually a lower engineering cost solution. So, for example, if you have an IEEE metal-clad switchgear, it has 7 standards. Well, that gear has to meet all 7 standards when you're engineering. On the IEC side, if you have 7 standards, you only have to choose 1 or 2. So there's less time involved and less cost from an engineering perspective. Let's talk about the performance of this. Now, we just touched base on the less land mass that it takes. Well, you still have to accompany the same amount of racks and cabinets inside the data center. So instead of going horizontal, they're now going vertical. And some data centers, typical, are going to be 2, 3, maybe 4 stories. There's now designs and infrastructure to go 8 stories tall. That's going to cause more megawatts needed to be used. And we're already seeing a transition from owners going, for example, from 30 megawatts per building to 60 megawatts per building. There's some instances where we're seeing 100 and plus megawatts per building. Now, you talk about renewable resources. That is starting to be a factor in the data center world. We are seeing a transition of owners switching over to solar and wind, but that varies per owner and per region. But as more local governments give tax incentives for new renewable energies being used, I think we're going to see an increase in that over the next 5 to 10 years. Back to you, Nathan.
Great. Thanks a lot for that detail, Joe. Appreciate it. So, Dave Helster, now that we've powered the data center, how do we keep up with the higher performance requirements? One of the significant tools that data centers are using to keep up with increasing demand is to increase their networking and their compute data rates. What is happening at TE to help meet these needs, and what is the magnitude of this task?
Yeah, thanks, Nathan. As you've heard already, the performance on data centers, the pressure, to increase compute power is being attacked from multiple angles, right? From, as Aaron mentioned, edge data centers, putting data centers closer to the end customer to increase compute. Doing things that are specific to workloads, right? Putting more AI into data centers. But one of the most common ways, that performance is increased, as you mentioned, is increase in speed, right? And what this does is it puts pressure on the broad data center, because you can't just increase the speed of one element. You end up increasing the speed of all elements. So processors and memory and storage, networking, they all have to increase together, or you end up having a weak link within the data centers. And what this means to TE is that we have to focus on a broad portfolio. We have to improve the performance to meet these speed requirements across many different products. Today, the industry is transitioning from 56 to 100 gig. And what this means is, characteristics like insertion loss and return loss, and crosstalk, these are all things that we care about, but now the frequency that we care about them increases. So instead of, a 12 gigahertz, care about, now we're increasing that to 28 and gigahertz and even higher. And again, just to emphasize that this speed increase, this performance increases across, a broad portfolio. And the ultimate goal is to, take the risk away from our end customers, so that, they're designing systems and, they know that they have a broad product portfolio from one supplier that can meet all the requirements.
So, David, help us understand, though. Is this just a matter of going to a higher number, or does it bring other complexities with it? I mean, help us understand the detail here.
Sure. Yeah. Of course, it would be nice if you could just turn up the dial on speed and everything, would be okay. But the reality is, increasing speed, brings with it many other challenges. For instance, when you increase speed, you're naturally going to increase the power dissipated, which puts significant challenges on the thermal design of the system. Other items such as EMI are just another example of some of the pressures that come with increasing speeds. And that's why, TE, tries to attack this problem from the customer's perspective, really from a system approach. For instance, as speeds get faster, often, the distance that you can go decreases. And, ultimately, we try to develop at TE, we try to develop new architectures and new ways of interconnecting things that take away those reach restrictions. Another example is, as the thermal design gets more difficult to implement, we embed thermal technology in some of our products. So not only are we solving, a performance, a signal integrity, issue, but at the same time putting a thermal solution together. So the end customer really solves two problems with one product.
Wow, that's cool, Dave. Thanks. So, Jonathan Lee, talk to us a little bit about connectivity. So within the data center, there's many miles of equipment connectivity. So this is a key area of focus for the cost effectiveness and yet high performance of the data center. How can this high performance connectivity be achieved in a cost effective manner? And can you talk a little bit about how TE is enabling this to continue to the next generation?
Sure. Thanks, Nathan. So, building on what the other speakers have said, one of the key things to consider as we talk about performance and cost effectiveness is thinking about how far we can stretch the passive copper channel, right? Dave just talked about the idea that as we go to these higher and higher rates, the links get shorter. Obviously, maintaining the higher performance over these links gets more challenging as we stretch performance. Now, the idea of sticking with this passive copper channel is that we reduce the amount of heat, we reduce some of the effects around the channel that are going to drive costs. And on the other side of it, we have fiber optics, which have a lot of potential, but come with a lot of cost, and they give you the flexibility of reach and performance, but they come at a much higher cost than that passive copper. So what we here have been doing, and as Dave and some of the other speakers will talk to, is how do we continue to stretch that copper further and further? And one of the key ways we're doing that, and the strategy that TE is employing, is moving into cabled channels, and that's where I come in with bulk cable. So the bulk cable approach is a key to that cost-effective strategy. Now, what is TE doing specifically to kind of help our customers in this area? Number one, and Dave touched on it, customer engagement. We have experienced and knowledgeable teams of FAEs and system architects who work closely with our core customers to understand their channel and system requirements as these links get shorter, and how they can better configure their channels to get as much out of those passive channels. Number two is the product portfolio we offer, right? And you can see it on the screen here, the wealth of content that TE offers for our customers, in their server, storage, and switch applications. Here, the architects that are working with the customers are not constrained to have to work, with different suppliers and different components. We have all of the content here at TE that we need to build those links. And then finally, you can see that there's a lot of cable, as I mentioned on this slide, in terms of connections, both for high speed and power. Our ability to have a vertical supply chain of critical components. We do make our own bulk cable. We have molding, stamping operations and manufacturing facilities. The ability to make our stuff in-house also helps us with maintaining that lower cost profile and gives us an advantage as we try to service our core customers.
Great, thanks, John. Mike Trice, let's go to you next. Based on the previous panel, we've heard a lot about higher data rates that are required, but how does this translate into specific solutions? Is it just more of the same devices going faster, or do the data centers have to enable alternative configurations on their way to meet these needs? And as these architectures shift, we hear that the higher data rates and the higher operating power bring thermal challenges as well. How does TE address that?
Yeah, thanks, Nathan. So as Dave and John and Aaron had all touched upon, right? Data center architectures are shifting all the time, really to do three core things, right? Maximize the capacity within a data center, minimize the cost of bit moved, and increase the equipment uptime. I think Dave's section highlighted the growth in compute bandwidth is driving the need for higher and higher I/O density. As you're able to move faster, now you have to get essentially higher volume of data in a smaller space, and that's where data center, particularly cloud data centers, are widely adopting the 8x112 QSFP DD and OSFP form factors to get that increased I/O density, so that they're able to achieve 12 terabits in one rack unit. While the speeds remain a major factor, as we've moved past 56 now through 112 and start considering 224 gigabits per second, right? Other factors are becoming critical to system designers. With the higher I/O speeds comes the penalty of increased power consumption, right? And the increased power consumption means the modules need to dissipate more power. And at 800 gigabits, a typical optics module in a QSFP DD or an OSFP form factor will dissipate upwards of 25 watts per port. That makes I/O the dominant power factor, the power consumption factor in many pieces of equipment inside the data center. The increased power dissipation, coupled with the higher density, makes thermal efficiency and thermal mitigation strategies a critical design attribute. TE brings to the table thermal solutions like its ZipperFin heatsink technology, our thermal bridge technology, and our thermal bridge heatsink technology to create reliable solutions. Because as the equipment gets hot, junction temperatures rise, reliability goes down. So TE helps drive system uptime to its maximum number. As another growing trend is in the DC power distribution, and large scale data centers, right, are moving to 48 volts for the DC power distribution inside the building. That reduces I²R losses by a factor of 16. And TE's busbar products are a key enabler to realize those efficiency improvements. With the increases to transmission rates, as John talked about, and Dave talked about the distances that we can move, in the copper world, whether that, it is greatly reduced, right? And particularly in circuit boards, to overcome that, we've seen an explosion of copper cable assemblies or twin-X cable assemblies inside the box, whether that be, TE sliver, OTB, or other internal cable solutions. We see, them overcoming the reach distance, right? And that's because the twin-X cable has essentially about a 5x improvement factor in unit loss versus the PWB materials, right? And that all boils down to a lower picojoules per gigabit per meter or centimeter, which is a key or a critical factor, considering the majority of the data center power is consumed by data, moving the data, not creating or manipulating it. So just to sum it up in a few short words, right? Today's architectures require a complete toolbox and a deep understanding. And while there's not a one-fit solution for the different types of data centers, whether it be cloud, enterprise, edge, right, they do have a lot of commonality. And TE brings, as Jonathan indicated, a full toolbox to be able to help deal with the challenges. Back to you, Nathan.
Thanks, Mike. So, yeah, this is getting interesting. So we've heard about powering the data center, but we've also heard from John and Dave and Mike that there's more power dissipation occurring within each part as well. And so it seems like we do need to worry about the power, the bandwidth, the connectivity of all these physical architecture demands. Let's talk about the data center trend to develop and deploy artificial intelligence and machine learning technologies. Chris Blackburn, can you explain to us, what do these technologies mean, artificial intelligence, machine learning, and some of the implementation hurdles to deployment? And how is TE helping to enable the use of these new technologies?
Certainly. Thanks, Nathan. So one of the biggest changes we've experienced recently is just the onset of connected devices in our lives. Mobile phones, household appliances, our cars, and millions of other devices are generating just an unprecedented amount of data. And insights from this data can have a direct impact on a firm's bottom line or to our personal lives. And whether it's increasing production efficiency, targeted marketing, financial analysis, or health tracking, artificial intelligence and machine learning is certainly making an impact across all market segments. And we've heard some discussion around on-premises data centers, hyperscale cloud data centers, and even edge data centers. And implementing and deploying AI hardware in any of these locations is certainly no small task. And we've heard the other presenters state, power delivery is absolutely critical. And our power connectors and cables ensure proper power delivery in these architectures at the rack level, chassis level, and component levels. And of course, a lot of compute power requires just a lot of power and generates a lot of significant heat. And as we heard Mike talk, the advanced thermal technologies from TE ensure that proper heat dissipation, enabling these critical components to operate efficiently over their extended lifetimes. Back to you, Nathan.
So, yeah, it's always tricky finding the mute button. So thanks, Chris. Another trend that we're aware of in the data center is this term called disaggregation. So talk to us a little bit about that. What does this mean, and what is required from a technology standpoint to implement disaggregation?
Yeah, so scalability and efficiency are certainly top of mind when we're deploying these AI architectures. And initially, common form factors were leveraged, like a PCIe add-in card. And this gave us the capability to add AI to existing server architectures. And as we scale up and scale out in these data centers, the approach there does not provide the efficiency that the hyperscale data centers demand. And we've seen a trend and a move towards more dedicated clusters specific for these types of workloads. And these architectures take a holistic approach from software to silicon to the complete data center architecture. And this is very similar to what we see in hyperscale cloud now. And in terms of disaggregation, one of the major things and challenges we have ahead is we have this hunger and appetite for more compute, processing more data, but we have a fixed power envelope within the data center. We can only house so many servers and so much equipment within a single data center. And really the challenge ahead of us now is how do we increase our resource utilization? So how do I boost servers from, say, being utilized 10% up to 50 or 60%? And that's just, doing more with what we have. And the trend here is software being leveraged to define and configure hardware resources on the fly. This is what we know as disaggregated architectures, where we have pooled resources, say storage, compute, or AI, machine learning, and they act as one. TE's broad portfolio of high-speed cables and connectors enables fast and reliable connections for these highly interconnected architectures to be realized.
Great. Thanks a lot, Chris. So I'll thank the panelists for all of the remarks that they've provided. We've talked about the growth of the cloud and how TE is helping to maintain the pace of that growth in terms of powering the data center, in terms of hitting the data rates and the technical challenges that come with those data rates, maintaining the cost effectiveness of the cloud, and many of the architectural shifts that enabled the continued growth and the TE technologies that the cloud is actually depending on to implement those new methodologies. Thank you again, guys, for taking the time. Now, let's open it up for some questions from our audience. And we got a couple power questions to get us started. So I'm going to turn to you, Joe. Can you talk about the percentage of owners that are switching to IEC gear, let's say compare 2019 to 2020, and also talk about how the mix of grid and renewables is being managed as well?
Thanks, Nathan, and both great questions. Touching base first on the mix and renewables and grid systems, unfortunately, that's a question that comes up quite often, but the percentage of projects using renewable energies today is less than 5%. So as the next few years go along and renewables become more prominent, we're going to be able to actually see what the reliance and reliability is going to be between a traditional grid system and a renewables energy system with that. So unfortunately, in the industry, there's just no definitive scientific answer to that. It's all mixed in what region that you're in and your local preferences and government preferences there. Going to the IEC gear, in 2019, we saw less than 5% of projects and owners were using IEC gear. However, in 2020, we actually saw a large increase to over 20% of projects were switching over to the IEC gear.
Wow, that's significant. Okay, another question. This one for you, Dave Helser. We've heard a lot of talk, there's some industry buzz about the transition from copper-based interconnects. What are TE's thoughts on that?
Yeah, over the years, there's been a constant balance between, copper and optics. And one of the questions I get very often is, what's the life of copper, right? Are we going to be able to continue to use copper? And, the fact of the matter is there's still a lot of life, in copper. And that's driven a lot by the cost benefits that typically are seen in, copper interconnects versus optic interconnects. And there's still a lot of, maybe tricks to play, right? The industry is looking now at even, 200 gig links, right? Single differential pairs driving 200 gig. Then you're using things like modulation and so forth to try to squeeze everything, out of it that we possibly can. But at the end of the day, there are limits to copper. As I mentioned before, there's retrade. You can only go so far when you increase speeds, and so at TE we're looking at both spaces. We continue to innovate in the copper space, try to push the limits, but we do have an eye on the optic piece as well. And I'll hand it over to Chris to maybe talk about some of the things we're doing in the data center to support optics.
Yeah, absolutely. So
So as Dave mentioned, right, it's really about reach, and we use optical technologies when we need to have that longer electrical and physical reach, right? So we talked a little bit about some of these AI architectures and more traditional network switching architectures, and really it comes down to cost optimization of these links. And you can imagine in some of these highly connected AI architectures, there are short links, connecting, say, chips to chips, and some of those may drive passive copper links. But as we extend those links and more optics are required, one of the things that the industry has its eyes on is where do we make this electrical to optical conversion? And in today's model, that is typically at the faceplate or the front panel of these chassis, servers and switches. Right? So we have chips driving electrical channels to the port, and pluggable transceivers making that electrical to optical conversion. And the larger overall trend is seeing that interface and electrical to optical conversion move closer and closer to the chips themselves, whether that's onboard optics or co-package optics. And the thing to push, and as we talk in standards forums and around industry, right? I think the maintaining shared footprints between copper and optics, whether we're making that electrical to optical conversion at the faceplate, on board or on the package, is really needed so that we can optimize these costs across these architectures.
So no end in sight is what I'm hearing. That the copper continues to be a vital solution. So thanks, Chris. Thanks, Dave. A reminder to our audience, feel free to use the Ask a Question box to send in some questions. We've got some good ones queuing up here. Mike Trice, as thermal loads increase, we may expect further use of liquid cooling in data centers. Do you think that this will be driven by data center infrastructure and utilities or through equipment design? Give us some comments on that question.
Yeah, so I think it is clear that as the power density continues its climb, right, there will be a brick wall that forced air cooling runs into, right, between the efficiency of fans, the noise generated by fans, right, and there's only so much heat load that forced air will be able to do, right. So it will start, and has already started in some parts of the network. In some parts of things, have already moved to liquid cooling. We see immersion cooling being used in some high performance data centers. We see cold plates used in some of the most sophisticated pieces of equipment today. But there's a 24x difference between the thermal conductivity of air and water, and so it's a natural progression that as these power loads move from a few hundred milliwatts per square centimeter to north of a watt per square centimeter, that there will be a transition, and that just maps back to the overall rack increases in power per square meter, right? If you go back a few years, the average power dissipation of a rack of equipment was below 10 kilowatts, and customers today are pushing 30 kilowatts with forced air. But as we move into the next generation, where more power dissipation, shorter distances, higher power densities, we're going to see a natural progression in the equipment manufacturers and the infrastructure to move to liquid cooling.
Thanks, Mike. Appreciate that. So sounds like that's a hot topic to watch. Sorry for the pun. Let's see. Dave, you and Chris talked about the fact that as we go to these higher data rates, the reaches become more constrained. How does that change packaging? Does TE have a play in terms of helping the customers with their packaging challenges, using TE socket technologies?
Yeah. So as I mentioned in one of my previous answers, we are definitely looking at different architectures, to try to help the end user, implement some the typical designs that they would have for their equipment, and that can be packaging of internal cables, as Jonathan mentioned. It can be putting sockets on packages to either get copper interconnects or optical interconnects closer to the chip. But really, a variety of different ways that we can approach it. And again, trying to take that systems approach, look at what the problem is that the customer has, and making sure that we have the right products to solve it.
Cool. Thanks, Dave. So I think, unless anyone's got another question that they want to enter in pretty quickly here, I think we've gone through the questions that came in from our audience, and we've almost used up all of our allocated time as well. So I want to thank our panelists for taking the time to be available today. Thanks for sharing your insights and for sharing insight into your activities, the different things you're doing to support the cloud data centers and the technologies that you're developing. We want to thank the audience for tuning in and joining us today. As mentioned earlier, tomorrow you will receive an email with a link so that you can watch an on-demand recording of today's session. Please do visit the registration page at www.te.com/techtalks to sign up for upcoming webinar events as well. We're always adding new programs, so check back often. Thank you all very much for attending, and have a great day today. Thank you very much. So long.